Hey guys, we're going to go over section 3.3, which is derivatives of logarithmic and exponential functions. I thought that this mean you would maybe appreciate it. Basically, today your goal is to try not to think about all the food you're going to eat so that we can learn a little bit about derivatives. Okay, so basically today's goal is to learn the derivative of logarithms and the derivative of exponential functions. Okay, pretty short and sweet. So I'm just going to go ahead and just give you a definition and tell you that the derivative of ln, natural logarithm, is 1 over x. And when I say 1 over x, I mean 1 over whatever's here. Okay, now understand that there could be a baby. Okay, so this first example we're looking at here is a mama baby. Okay, so I'm going to start by saying, what's the derivative of mama? And the derivative of mama means what's the derivative of ln. So using the formula up there, the derivative of ln is 1 over and whatever your baby is. Okay? Multiply by the derivative of your baby. So what is the derivative of x to the third plus 1? That should be 3x squared. And we're just going to simplify. And there's not a whole lot of simplifying you can do other than put 3x squared on the top and x to the third plus 1 on the bottom. So that would be your answer. Okay? Short and sweet. Here's another way that you can describe a mama-baby derivative. So this is basically just saying, what's the derivative of ln u? Well, it's 1 over u, meaning 1 over whatever the baby is, times du dx. That just means the derivative of the baby. Or in this case, baby is called u. Okay? Just another way to write a derivative formula. I just wanted to show you what that could look like. So the derivative of ln of sine x. So sine x is our baby. Ln is our mama. Here we go. The derivative is 1 over sine x. That's the derivative of the mama part. Times the derivative of baby, which is cos x. Now, because this is a trig question, we can do a little bit more other than just putting it into one fraction like we did before. What we could do here is say that cosine over sine is the same as cotangent. Okay, so make sure that you understand that connection there. Example 4, differentiate the square root of ln. Remember, anytime we see square roots, if we have to take a derivative, it's helpful to rewrite it as that thing to the 1/2 power so that you really understand like what your derivative is going to look like. So this time I do have a mama baby. Mama is the 1/2 power and baby is ln. So let's start with mama. Derivative of mama is 1/2. Keep your baby to the negative 1/2 power. That's the derivative of mama times the derivative of baby. What's the derivative of ln of x? Is 1 over x. Put it all back together. So we would have a fraction. I think the only thing on the top of the fraction is a 1. 2 would be on the bottom. X would be on the bottom. And ln x to the 1/2 power would mean a square root. So that would be the most simplified answer you could get. All right, to do this next example, we need to know more. We only at this point know how to find the derivative of ln, and this time we have a logarithm with base 10, so not the same thing. So I'm going to show you something we did last year that's going to help us here. It's called change of base. So change of base is a little formula typically that you use to be able to solve logarithms with a calculator. But this time we're going to use it to help us take the derivative. So the way that this works is if you have log base anything, you can change it to ln of the inside number over ln of the base. And we're going to do that here because I need to take the derivative of a logarithm, but I don't know how. But if I can change it to lns, then I can figure out how to take the derivative, okay? So we're going to do that. Let's do change of base. All right, so change of base says that I could take ln of all this stuff on the inside, so ln of 2 plus sine x, and divide by ln of the base, which is 10. All right? Still looks like it's going to be complicated. And actually, some of you are probably thinking, oh man, like I got to do stupid quotient rule for this. You actually don't. Here's why. If you think about it like a multiplication problem, which is what I'm going to do, I could separate this and call it 1 over ln of 10 times ln of 2 plus sine x. Well, why would I do that? Well, 1 over ln of 10, this is really just a constant value. It's just a number, okay? There's no letters in this, so I could treat it like a constant. And that means I can take the derivative over here and just multiply my derivative by that thing, okay? So that's what I'm going to do because I really would like to avoid quotient rule at all costs. So I'm going to take my derivative. Wait a minute, I just realized I did something stupid. I don't know where I put derivative here. This is not the derivative. It's just the original thing. All right, so I'm going to take the derivative. I'm going to leave 1 over ln 10 out here. Now I'm going to take the derivative of ln of 2 plus sine x. So that would be 1 over 2 plus sine x times the derivative of baby, which is cos x. I'm going to put it over 1 so I can see everything all together. And let's clean this up. So my answer, if I clean it all up, would be cos x over ln of 10 times 2 plus sine x. Okay. We basically just used this formula that's written here. And this formula is like a shortcut for all this work that I did on this example back here. So essentially I'm giving you options. I'm telling you that if you need to take the derivative of a logarithm with a base, you could just use this formula. Or you could just do what I did and do change of base. Come on. Do change of base and go through it that way. I personally don't really care which way you do. Just pick one and make sure that you do it correctly. I wanted to show you real quick why you don't have to memorize this formula like one more time. So what I was saying is I could, instead of memorizing another formula, I could rewrite it as log base x over, not log, ln of x over ln of a, and then do the derivative of that. So really that's the same as 1 over ln a, which that's just a constant because a is a constant value, times ln x, and the derivative of that would be, you would leave the 1 over ln a alone because it's a constant, multiply by the derivative of ln, and then just kind of put it all together. And that's where this formula is coming from. Okay? All right, let's see something that is a little bit messier, just so you know what to expect. Okay, So this example looks like, when I first look at it, it looks like mama baby, with mama being ln and baby being the fraction. And you're right, it could be. But we can do something a little bit different, and actually it's going to save you a tremendous amount of time if you can catch this in advance, okay? There are properties for logarithms that we went over in the last section. Use those properties to help you before you take the derivative, okay? So what I can do is say, all right, logarithms, if I see a fraction inside of a logarithm, I can break it up into two different logarithms. So this is not me taking the derivative, by the way. This is just me rewriting the equation to make it easier to take the derivative. Okay, now, if you don't want to do this, that's fine. You could go ahead and do mama baby with a quotient rule inside. Good luck. That would be really painful and awful. However, if you can kind of stay with me for a minute and watch these properties, it's going to save you so much time. Here's what I do. I would say quotients equal subtraction in logarithm world, which means I can break this up by putting ln of x plus 1 minus ln of x minus 2. I'm going to write it as x minus 2 to the 1/2 power. Okay, that's step 1. I can do more. I can also take this power and move it to the front of that particular piece. So I still have ln of x plus 1 minus 1/2 ln of x minus 2. Okay, again, I have not yet taken the derivative. I'm just rewriting using logarithm properties. Now I want to take the derivative. Now look what I've done. I've eliminated the quotient rule, and I've eliminated the mama baby that would have been this 1/2 power here. So now I can say derivative of ln of x plus 1 would be 1 over x plus 1 times the derivative of baby, but that would just be 1, so it would just be that, minus 1/2 times the derivative of ln of x minus 2 would be 1 over x minus 2 times the derivative of baby, but again, that would just be 1, so I can just leave it here. And then I'm just going to do one little thing to clean it up, and that is I'm going to put the 2 on the bottom with the x minus 2. See how easy that is? If you can catch the properties ahead of time, saves you so much time. Okay, we're also going to learn how to do something called logarithmic differentiation. So what I'm going to do is I'm going to start by saying, look at how awful this problem is, right? It is awful. You do not want to have to do product rule and quotient rule and mama baby all in one step. It would be a nightmare. Insert logarithmic differentiation. Okay, so logarithmic differentiation is built for things like this. It is meant to give you another way to take derivatives of things that are really complicated, specifically things that are quotients and products. Okay, here's the idea. The idea is, okay, if I actually had a logarithm in front here, I could use those logarithm properties to break all this up like I did in that last example. You can put a logarithm in front of this problem if you do it on both sides. So that's what we're going to do. By the way, up here is a step-by-step process if you are somebody who likes that sort of thing. So what I'm going to do is I'm going to take the natural log of both sides of my equation. Actually, I'm going to go ahead and rewrite the radical while I'm at it. So I'm taking the natural log of both sides. Okay, that's step 1. Step 2 is take the derivative. I'm sorry, not take the derivative. Step 2 is break this up now using your logarithm properties. So I have a product on top that could be turned into a plus. Quotient is minus. Exponents come to the front. Do all those properties on this complicated side. So I would have, I'm going to do all this in one step just to speed up this process, but I'm using all my properties at one time here. So using my properties, this is what I would end up with. Now you're going to take the derivative of both sides of your equation. And this is where you're going to use implicit differentiation, okay? So this is where we are going to take the derivative with respect to x. And remember, if your variable is not an x, you're going to have to include dy dx in that location. So right here off the bat, what's the derivative of ln? It would be 1 over y, but because this is a y, I need to put dy dx, and that actually should be the only place that I would need that here. Derivative of 3/4 ln would be 3/4 times 1 over x. Next part, my derivative would be 1 over x squared plus 1 times 2x, because that's the derivative of the baby. And then at the end, 5 times the derivative of ln of 3x plus 2 would be 1 over 3x plus 2 times 3, because that's the derivative of baby. Okay? I know this is still a messy problem, but it is still a ton easier than doing product rule and quotient rule and mama baby all in one. Okay? Because now all we got to do is clean it up. So one thing at a time. You have 1 over y dy dx. I'm going to call this 3 over 4x. In the middle here, these 2's would cancel because one's on top, one's on bottom. So really this would just be x over x squared plus 1. And then over here I can multiply the 5 and 3 to make it 15 over 3x plus 2. Okay, you're almost done. The only thing you have to do now is solve for dy dx, because dy dx is the derivative. So to solve for dy dx, you're going to multiply the y to the other side. So you have y times all this stuff. And then we're going to do one small thing at the end, okay? This answer would be totally fine, but you can do more this time because you actually do know what y is. If you go back and look, you had an equation for y that was the original problem. Y equals that big messy fraction. So in place of y, you can put that big messy fraction back in its place just to give you a derivative where everything is in terms of x. That's the whole point of that last step. So my final answer is going to be quite a lot of stuff. But again, the whole point is we want the derivative to be all x values just to make it kind of more cohesive. Real quick reminder, we use this technique called logarithmic differentiation to help us when a regular derivative would have been a really big disaster or a really big mess. Okay, on to derivatives of exponential functions. So, how would I find the derivative? Any ideas how I could find the derivative of something like this without knowing a formula? Well, what you can do is use logarithmic differentiation like we just did. Okay, so watch this. I'm going to apply a logarithm to both sides of my equation. I'm going to use my logarithm properties to simplify on the right side. So I can bring the power to the front. Okay? Now I'm going to take the derivative on both sides. So on the right side, I would have 1 over y dy dx. On the right side, ln of a is just like a number. So really, x ln a is the same as having something like 5x, just a number with an x. What would be the derivative of 5x? That would just be 5, right? So what would be the derivative of ln a x? It would just be ln a. Okay? Multiply the y over, and you get y ln a, and then plug in what y was equal to. Y was equal to a to the x. So you have just created a derivative formula for a to the x. The derivative would be a to the x times ln a. Again, it's kind of one of those things that you can memorize if you want to, or you could just use logarithmic differentiation to find the derivative. It doesn't really matter. I'll show you both ways, the memorizing way and the not memorizing way, and you can decide what you like better. Doesn't matter to me. Okay, so I'm going to show you over here. Let's do it the formula way. So find the derivative of 10 to the x squared. So I would say, using my formula way, the derivative is a to the x, which that means kind of like the equation itself, 10 to the x squared, times ln of a, and that would be ln of 10. This particular problem also has a baby. X squared is the baby. So you would also have to multiply by the derivative of baby. So if we clean all this up, it would be 2x ln of 10 times 10 to the x squared power. Really odd looking, but that's it. All right, let's do this problem again, but let's do it the logarithmic differentiation way. Okay, so what I could do is write this as y equals 10 to the x squared power. Apply a logarithm to both sides. Use logarithm properties to clean this up. So bring the exponent to the front, like x squared ln 10. Take the derivative of both sides. The derivative over here, remember ln 10 is just a number. So really let's start with what's the derivative of x squared. That would be 2x times ln of 10, because ln of 10 is just a constant value. Multiply the y over. And then substitute your y value back in. So my derivative would be 10 to the x squared power times 2x times ln of 10. So same answer on both sides. They're in a different order, but either method works. Again, I kind of prefer not to memorize formulas. So I like the right side, but the left side is fine too. So up to you. Okay. What about if the value of a is equal to e? So let's talk about what happens if we're looking at e to the power of x. So I know that the derivative of a to the x equals a to the x ln a. So let's change it and see what would happen if a is equal to the value e. So everywhere you see an a, put an e. Well, then it would make sense that the derivative of e to the x is e to the x ln e, right? Except, I don't know if anybody caught this or not. What's ln of e? Ln of e is equal to 1. Ln of e is equal to 1, okay? So that means that the derivative of e to the x is e to the x times 1, which is just e to the x, okay? This should be your favorite derivative on the planet because it's literally so simple. The derivative of e to the x is itself, e to the x, okay? So let's see how this derivative thing would work if it's the same. This one is obviously a mama baby. So mama is going to be e to the x and baby is going to be tangent. So when you take the derivative, start with mama. Derivative of mama is e to the x, but we're going to keep the baby. So same thing. Times derivative of baby is secant squared x. And I guess the only thing you could do if you really want is rearrange it and put secant squared x at the beginning, but that's about as nice as you can make that one, okay? Let's try one more. Actually, we have two more. A little bit more complicated, just so you're prepared for whatever comes your way. This is a product rule. So we have e to the negative 4x multiplying sine of 5x. So we're going to do product rule for this guy. Okay, when we get to the first part, u prime means the derivative of e to the negative 4x. So that would be e to the negative 4x times the derivative of baby, which is negative 4. So that's all u prime times v plus u times v prime. So that would be cos of 5x times the derivative of baby is 5. Let's clean this up a bit. In this first section, I can just move the negative 4, maybe also the sign to the front. In this back section, I think, again, just move the 5 to the front so that cos of 5x is at the end. That's about all you can do. Now we're on our last one. Okay, also with this question, you could try to do the formula way, where you're going to use the derivative a to the x is equal to a to the x ln a, or you could use logarithmic differentiation and just kind of say, this is messy, I'd rather just do logarithmic differentiation to get to the point. Let's see. So I'm going to go ahead and do ln of both sides. Which is going to allow me to use logarithm properties. Okay, now my next step is to take the derivative of both sides. But on the right side, this time we have x's in two places. So we are going to have to use the product rule to take the derivative over there. So left side is just going to be 1 over y dy dx. But on the right, I'm going to have to do product rule. So quick reminder, radicals equal that thing to the 1/2 power. So u prime is 1/2 x to the negative 1/2 times v plus u times v prime, which is 1 over x. Let's just kind of try to clean it up a little. ln x over 2 radical x is what that first part would be. Actually, over here, I can subtract these exponents to make it simpler. So x to the 1/2 times x to the -1 technically would be x to the -1/2 power, right? Yeah. And then that actually means I would have 1 over square root of x. So I'm going to go ahead and write it like that. 1 over square root of x is how that would reduce. And then you're going to multiply your y over. That is a weird looking 2. Hold on. There we go. I suppose if you wanted, you could do a common denominator situation there, but no need. Last step, plug in the y value, right? And y was x to the power of radical x. So x to the power of radical x goes out here. And that's about all you got to do. If you are somebody that thinks the formula way would be better, I encourage you to try this problem with the formula technique and see if you get an answer that's algebraically equivalent to this one.